is designed to give you an overview of information in Module 4B of our course. Module 4B includes air and water pollution, solid waste disposal, and toxicology. Before we move further into understanding pollution and waste, it is important to look at several general concepts. These concepts include the ways in which we categorize pollutants. We categorize pollutants in one of four ways: by their location of origin, their type of origin, their lifespan, and their reactivity. In terms of location of origin, we identify pollutants as either point or non-point. Point locations are those that we can trace back. We can tell you exactly where a particular pollutant came from. Non-point pollution are those pollutants that we cannot trace back to a very specific source. They tend to come from abundant areas such as motorways and cars, or large areas such as farms. Additionally, we generalize and categorize pollutants by their type of origin. Are they agricultural, industrial, or urban and domestic related? Additionally, we talk about their lifespan. This is also known as their persistence, or how long do they stay in the ecosystem. There are four basic categories of lifespans for pollutants. Persistent pollutants remain in the ecosystem for an incredibly long amount of time. The most common of these are things like heavy metals, like lead. You have degradable. These pollutants are able to be broken down by natural processes, but it takes a specific amount of time. Non-persistent pollutants are those that are removed from the ecosystem very quickly. And biodegradable pollutants are a very specific kind of degradable pollutants. In order for something to be considered biodegradable, it must be able to be broken down by the metabolic processes of a living organism. Lastly, we categorize pollutants by their reactivity. Primary pollutants are those that are released directly from the source. Secondary pollutants are formed from the reaction of multiple primary pollutants in an area of a sink. This diagram shows you some examples of point and non-point pollution sources. You can see in the top right of this image that you have city streets, rural homes, croplands, and animal feedlots, as well as suburban development that all contribute to non-point pollution sources. It's also important to note that there are multiple locations of origin here, showing industrial, rural, and agricultural sources. At the bottom left, you'll see the point sources, which are factories, and in this case, a wastewater treatment plant. Let's do a quick overview of the components of pollution that we're going to discuss. We are breaking pollution down into two separate categories: aquatic and atmospheric. When we talk about aquatic pollution, we're typically talking about either surface runoff, stormwater runoff, or wastewater. Wastewater is looked at in terms of whether it's coming from a municipal wastewater system, such as sewers, or if it's coming from an individual home in terms of septic tanks. Wastewater that is used municipally tends to be treated. We also have to talk about regulations that are responsible for maintaining water quality. These include the Clean Water Act and the Safe Drinking Water Act. When we talk about atmospheric pollution, we're talking about pollution based on its source and its reactivity. Sources are defined as being either natural, stationary, or mobile. Reactivity is defined as primary and secondary, and the regulations we have to address are the Clean Air Act and Let's look at the types of aquatic pollution. Surface runoff comes from impermeable surfaces that prevent infiltration. This can come from overflowing and flooding of bodies of water. It can come from dumping of water, and it can also come from precipitation. In surface runoff, you typically get solid materials, soil, debris, animal waste, and oil and gasoline from cars. Stormwater runoff is closely related. This largely comes from massive amounts of precipitation, and it's caused by impermeable surfaces preventing infiltration. And it becomes a much bigger problem when there is inadequate drainage, which is associated with municipal sewer systems. Wastewater is made up of black and gray water. Black water is water that comes from the toilet and is having come in contact with human waste, specifically feces. Gray water is water that comes from things such as your sink, your bathtub, or your washing machine that can be treated and used for other things, such as watering your plants or washing your car. Wastewater, in this case, we're talking about coming from homes and industry. This is your typical municipal sewer wastewater treatment. When we talk about municipal sewers, we're talking about those in which the city provides water for an individual and then takes that water away through a sewer system. There are two types of municipal sewers. There are dedicated sewers and combined sewers. A dedicated sewer only moves wastewater. It does not provide for the capacity of overflow or stormwater runoff. With a dedicated sewer line, it's very common that you will have overflow during large rainstorms, which can overwhelm the capability of your wastewater treatment system, leading to large amounts of pollution ending up in your water sources. A combined sewer system has the capacity to handle stormwater runoff. Areas that have combined sewer systems also have much more adequate drainage throughout their city area. Let's take a quick look at the kinds of wastewater treatment. It's important to note first that there are three separate stages associated with wastewater treatment in almost every area. Those are primary treatment, secondary treatment, and bacterial disinfection. Note that there is sometimes a thing called tertiary wastewater treatment. This is a separate entity that is found very rarely, as it is extremely expensive. Let's talk through those three types. When you look at the diagram you see here, stages 1, 2, and 3 are considered primary wastewater treatment. Primary treatment is largely a physical process. This physical process requires bar screening, or the removal of large debris through a screen. Once that large debris is removed, the water moves through to what's called the grit removal, or the settling tank. Here, you will have large areas of water that is allowed to settle and sit still to allow materials such as sand and grit to fall to the bottom. That is then skimmed out, and the water is moved to what's called the primary clarifier. Here, the water again is allowed to settle, and any additional materials are removed from that stage. Remember, stages 1, 2, and 3 are physical processes, and these are your primary wastewater treatment steps. Any of the grit and material that settles out in stages 2 and 3 is sent to what's called the sludge tank. And the sludge tank is used for multiple practices later on in the process. After stage 3, we move into the secondary treatment process, which is largely a biological process. In stage 4, the water is treated with what's called activated sludge, which allows bacteria to grow and be able to break down the materials that are in the water. It's typically treated with large amounts of oxygen in this aerated process to allow for this decomposition to take place. After the aeration, we move into the secondary clarifier. This allows the water once again to settle, to allow materials to rise to the surface to be skimmed off, or fall to the bottom to be removed to the sludge tank. This is the end of secondary treatment. After secondary treatment, you move into the disinfection stage, which is in this diagram, stage 6. Typically, the disinfection stage is treatment of the water with either high-quality UV light or chlorine treatment. After chlorination, the water is moved through another system for final approval, where testing is done to make sure that all of the components are within regulation, and then the water is released through an effluent pipe back into your water system. The sludge that is found in the sludge container is often dried and either taken to a landfill or used as fertilizer on agricultural fields. Remember, I said that there is sometimes a tertiary stage. The tertiary stage is expensive because it is designed to remove very specific pollutants, such as nitrogens, phosphates, or different kinds of medication that may be found in the system. This is incredibly expensive, and very few places throughout the world actually use it. This is a simplified diagram of the one we just saw. Notice that it includes chlorination, or the disinfection stage, as the very last part of secondary treatment. This is accurate. The important thing to note is that tertiary treatment is a separate process and is very rare because it is typically associated with very specific pollutants. The goal of primary and secondary wastewater treatment is to remove large debris, sand and grit, and to remove human waste. Some homes are not connected to a municipal sewer system. Instead, they have a septic tank. A septic tank is a large holding tank that is placed underneath the ground near the house, where all of the water is going to be pumped toward. So when someone in a house with a sewer flushes their toilet, runs their sink, or washes clothes in a washing machine, all of the water that drains out goes into the septic tank. The septic tank is designed to allow water in and water out. While the water is in the septic tank, the solid sewage will typically fall to the bottom, and you will have scum or materials that can float that will rise to the top. If a septic tank is properly maintained, the biological activity is enough to keep the solid sewage to a very low level, allowing the water to freely move in, settle, and then move out. The water will then move out into a field that allows for the water to filter through and will eventually move through a gravel or crushed stone process and will eventually work its way back into the groundwater. However, when there's not enough biological activity in the septic tank, the solid sewage can build up, which will eventually cause the septic tank to overflow and will require massive amounts of reconstruction of the yard and possibly a replacement of the septic tank entirely. Aquatic pollutants. We have solid waste, which is typically debris, trash that will find its way into the water systems. When we're talking about debris here, we're talking about things like limbs, leaves, and other larger components. Organic waste coming from animal or human feces. Because these are very high in nitrogen and phosphorus, this can lead to cultural eutrophication and the development of dead zones in estuaries. One of the major components or major dead zones that we have is in the Gulf of Mexico, where the Mississippi River empties out. The Mississippi River carries large amounts of organic waste that ends up in the Gulf of Mexico, and then the organisms there will tear through that organic waste until they eventually reach a point where they can no longer support their population, and you get what is called an anoxic or an oxygen absent environment, also known as a dead zone. Organic waste also comes from what is called a persistent organic pollutant, or a POP, P-O-P. Examples of these are DDT and other components that are listed in the UN Dirty Dozen list. Persistent organic pollutants are incredibly dangerous because they are almost exclusively fat soluble, which means that they will bioaccumulate in the fat cells of an organism, and as that organism is eaten at higher levels of the food chain, that pollutant will not only bioaccumulate in their bodies, but it will also biomagnify as it moves up the food chain, becoming more and more concentrated as it reaches the top. You also have your inorganic compounds, which is the NPKs that we've talked about, and you'll have thermal pollution, either coming from wastewater treatment or more commonly from areas such as nuclear power plants. One of the major problems that we see with aquatic pollution is what is called biological oxygen demand. We know that the large majority of organisms that are in our water, especially our flowing water, are aerobic organisms. They require oxygen in order to do their cellular respiration processes. We also know that their metabolic process is often associated with things like nitrogen, potassium, and phosphorus, as well as carbon-based materials. Here we see a flowing river. And what we're going to look at is what happens when you have organic waste dumped into this system. So you'll notice that there are two lines. The kind of orange line at the top is showing you your concentration of oxygen. The blue line is showing you your biological oxygen demand, or the rate at which these organisms are using oxygen. Note that normal, healthy river systems and bodies of water typically have about 8 parts per million of dissolved oxygen. So let's start at the beginning. So in the clear zone, you have normal water organisms that are supposed to be there. These ones that survive in a very healthy ecosystem, clear water, the turbidity is very low. You have appropriate dissolved oxygen and dissolved carbon dioxide, appropriate pH, temperature, those kinds of things. All right. We have at some point the wastewater or the organic waste dumped into the system. And that ends our clean zone and starts what's called the decomposition zone. In the decomposition zone, because there is now all of this organic material for these bacteria to work with, the biological oxygen demand shoots up dramatically. The organisms in the water start doing this breakdown process and they start using more of the oxygen. So your biological oxygen demand is going up, your dissolved oxygen is starting to go down. Once we move from the decomposition zone, okay, and in the decomposition zone, we're getting organisms that work really well in moderate oxygen concentrations and also are much more tolerant of different qualities of the water that make it not necessarily the best to live in. So we move from the decomposition zone into what is called the septic zone or the anoxic zone. This is because your dissolved oxygen drops dramatically. It drops to 2 parts per million, which makes it very, very difficult for anything that is aerobic to survive. So the septic zone is made up largely of anaerobic organisms like fungi and sludge worms and bacteria. Okay? But you'll notice that your biological oxygen demand is starting to decrease because the majority of this organic material has been broken down. Once we leave the septic zone, we move into the recovery zone. Here we have a return of those things that we call the trash fish, those things that are able to survive in transitional dissolved oxygen concentrations. It's in the recovery zone that your biological oxygen demand begins to drop and will eventually reach its original concentration, its original rate. And then your dissolved oxygen begins to go back up because it's not being used as much, so it can replenish. And then we move back into the clear zone. The clear zone, we have our normal clean water organisms with a low biological oxygen demand and a dissolved oxygen that is up to 8 parts per million once again. Here are some of your common measures of water quality. Remember, we have turbidity, or how clear is the water. Salinity, what is the salt content? Total dissolved solids, what is actually suspended in the water, and how much of those are there? Conductivity, how well do the ions in this aquatic solution transfer electricity? What is the pH? What is the temperature? What's the biological oxygen demand? What is the dissolved oxygen and the dissolved carbon dioxide? And if this is a moving body of water, what is its flow speed? All of these characteristics are what we look at when we talk about whether or not a water system is clean or whether it has high or low water quality. Water quality in the United States is regulated by two major laws. The first is the Clean Water Act, which was originally passed in 1972. The Clean Water Act sets requirements for the clarity and quality of water that occurs in a natural location. So in this case, we're looking at what is the water in a river system. And wastewater that is dumped back into a river system is subject to these laws. The Clean Water Act has been amended multiple times, both for the good and for the bad. In 1974, the Safe Drinking Water Act was passed, which is a tack-on of the Clean Water Act. This sets requirements for quality and content of publicly provided drinking water. This does not apply to home well systems, but if you have municipal water, you have to know that your water system is meeting the requirements of the Safe Drinking Water Act. Is it easy to get by this? Sometimes it is. Flint, Michigan is the keystone of understanding that the Safe Drinking Water Act doesn't always live up to what it's supposed to do. Now that we've talked about aquatic pollution, let's take a step forward and talk about atmospheric pollution. When we talk about atmospheric pollution, we're talking about things that come either from mobile sources, stationary areas, or natural sources. Mobile sources, of course, are cars, trucks, buses, motorcycles, airplanes, all of those things that are moving. Stationary area tend to come from large places that don't move. And then you have your natural sources, such as volcanoes, wildfires, and lightning strikes as well. In addition to identifying an atmospheric pollutant based on whether it is mobile, stationary area, or natural, we also talk about it in terms of primary and secondary pollutants. Primary pollutants are those ones that come directly from the source. And this diagram here shows you some of the most common primary pollutants. Carbon monoxide, carbon dioxide, sulfur dioxide, nitrogen oxide and nitrogen dioxide, the majority of your hydrocarbons, and particulate matter. Any of these primary pollutants can interact with each other and with sunlight and will form secondary pollutants, such as multiple acids, such as sulfuric acid, SO3, tropospheric ozone, and photochemical smog, and your acid rain components. One thing to note with the primary pollutants, you have this thing called a volatile organic compound, or a VOC. This is often released from automobiles, and it is one of the hydrocarbons that's released. This diagram breaks down some of the major atmospheric pollutants that you will see. Carbon monoxide, carbon dioxide, and nitrogen and sulfur oxides almost exclusively come from the burning of fossil fuels in industry or in the use of automobiles and other transportation processes. They are very particularly primary pollutants. You may have ammonia, which is one of those volatile things. Then you have volatile organic compounds, POPs, ozone, particulate matter, heavy metals. For particulate matter, it's important to understand that there are two kind of types of particulate matter. There's PM10 and PM2.5. The PM stands for particulate matter. The 10 and the 2.5 talk about its diameter. And when we're talking about diameter, we're talking about nanometers. Very, very small. So PM 2.5 is incredibly small, and it's very easy for it to get into your lungs and can cause lots of health problems as well. One of the things we identified on the very first slide for atmospheric pollution was that ozone is a secondary atmospheric pollutant. When we talk about ozone, remember there are two types. There is stratospheric ozone, which is formed and broken down in the stratosphere through the interaction of oxygen molecules and free oxygen atoms and ultraviolet light. Stratospheric ozone is good. That is the ozone we need to protect us from UV radiation. Tropospheric ozone is bad. Tropospheric ozone is a pollutant. Tropospheric ozone typically forms from nitrogen oxides and VOCs in the atmosphere that interact with sunlight and form O3. That O3 is a major component of what we call photochemical smog. So remember, in the troposphere, VOCs and nitrogen oxides are going to interact with sunlight and form tropospheric ozone, which can go on to become part of photochemical smog. In the stratosphere, ozone is formed through the interaction of O2 and free oxygen atoms and sunlight to form the ozone that we need to protect us from UV radiation. Tropospheric bad, stratospheric good. In addition to understanding the common atmospheric pollutants and the way in which they work together to be primary and secondary and form components like tropospheric smog, tropospheric ozone, and photochemical smog, we also have to think about the fact that there is a difference between indoor and outdoor pollutants. While outdoor pollutants tend to be ones that we think of as more dramatic in terms of problems, that's actually not the case. Indoor air pollutants are typically more damaging to our health, largely because we are exposed to them much more often and they are more concentrated because they're held within a confined space. There are multiple types of indoor air pollutants. You can have radon, which is a radioactive gas that comes from the breakdown of rock. You can have dust, dander, dust mites, pollen if you have plants in your home, disinfectants, solvents, cleaners, gas if you have a gas stove or gas heating, carpeting. There are a large amount of things indoors that will release air pollutants, and one of them is kind of these volatile organic compounds, which we will see here as things like formaldehyde and other aldehydes that come from new furniture, come from carpeting, and can even come from, if you get your clothes dry cleaned, it's going to come from that as well. So while outdoor air pollutants are on a larger scale more damaging to society as a whole, we're also looking at indoor air pollutants as being a big problem as well because they are concentrated and we are in contact with them much more often than we are in those that are outside our homes. One of the problems associated with indoor air pollution is sick building syndrome. Sick building syndrome is a series of symptoms that occur when an individual is exposed to a contaminated space. Most often, sick building syndrome is associated with very old homes and businesses and buildings or very new ones. They're most often caused by inadequate ventilation and some kind of chemical and or biological contaminants. Most often, it's going to come from paint fumes. It may be lead-based paint if it's an old home or an old building. It could come from formaldehydes and other volatile organic compounds that come from new furniture where those materials have been treated with formaldehyde as a preservative to prevent insects and other things to kind of eating the materials. You are probably very familiar with this kind of formaldehyde-y smell. You probably don't know it. It's what you smell when you smell new car. That is kind of like the preservative treatment materials that are used that can contribute to sick building syndrome. So how does one know they have sick building syndrome? The big tip-offs are headaches, nausea, kind of blurry vision, kind of a burning sensation in the nose that go away almost immediately upon leaving the building that you're in. So if you are experiencing those kinds of symptoms and they come and go, and the coming and going is dependent upon whether you're inside the building or outside the building, that's a pretty good indicator that you have sick building syndrome. Atmospheric pollution that we have to talk about are noise and light pollution. These are more common in areas that are highly urbanized, but can be a problem in rural areas depending on location. The human ear is designed to hear very specific noises and to hear those comfortably. For the most part, around 70 decibels is the common area of which we hear and we can be comfortable with. This is typically about the noise level that you would find in a business office or around a street traffic area. As we move further up on that decibel level from that 70, you begin to hear things that are much more concentrated in their decibel level and have higher incidences of causing hearing damage. By the time you get up to a jet engine, which is 140 decibels, it's double the normal amount that you would hear. This will cause physical pain, not just hearing damage. You will physically hurt. So when we have these urban areas that are highly concentrated, like New York City, for example, and you have traffic going at all hours of the time, you have these jet engines from LaGuardia and from JFK, and then you have these jackhammers on the street when we're doing construction. All of this builds up into this kind of noise drone that can weaken your hearing, especially with long time exposure. However, short-term exposure can cause hearing damage as well. But in addition to noise pollution in an urban area, you also have light pollution. And light pollution is when it's impossible to see the dark night sky as it actually is, because the haze of ever-present fluorescent lights kind of blocks that. It's hard to see beyond the haze of light from the urban area to what the sky actually looks like. So in order to really see that, you would have to completely leave an urban area, an inner city area, and you would have to go almost into a wilderness zone in order to be able to see the sky for what it actually is. Because that light pollution is so diffused, especially on the east coast of the United States, it's almost impossible to see the night sky as it actually is. And that can lead to sleep disturbances as well as with the noise pollution as well. Because your body, your circadian rhythms have trouble figuring out, is it daytime, is it nighttime, should I be asleep, should I not be asleep, with those large amounts of light. What are the regulations for air quality? The first and most common is the Clean Air Act, which was originally passed in 1970, which has been amended multiple times. The Clean Air Act regulates the emissions and concentrations of components in the atmosphere, applying specifically to industry and transportation. Later on, we had the addition of these things called the Corporate Average Fuel Economy, or CAF standards. And it was passed in 1975 when we talk about the Iran oil embargo, which made it very difficult to get gasoline for transportation. So this law was passed directly in response to that. And it requires light transportation vehicles, which are considered those that have a gross weight ratio of less than 10,000 pounds, to have an average mile per gallon of 27. Okay, so that sets the fuel efficiency level for light transportation. There are a large amount of materials and transportation vehicles that are over that GWR of 10,000, to which the CAF standards don't apply. So it's possible to get around this, and companies will do this so that they don't have to go through this kind of process. They will make the car slightly bigger. You're looking at trucks, those ones that have like 8 wheels, which it's a pickup truck that has 8 wheels. It's ridiculous. That will be exempt to that kind of law. We've talked about aquatic pollution. We've talked about atmospheric pollution. Let's talk about the kinds of pollution that we find on land. We're going to talk about solid waste. There are 3 different categories of solid waste that we will discuss: municipal solid waste, or MSW, industrial waste, and hazardous waste. Municipal solid waste is looked at in terms of coming from homes and small businesses. So we're not talking about industry, we're not talking about agriculture here. The components, most municipal solid waste is made up of things that are either recyclable, compostable, or are trash. And when we talk about disposal of municipal solid waste, we're talking about using landfills, incineration, or transport. Industrial waste is made up of chemicals and machinery. And hazardous waste are those things that are considered flammable, toxic, corrosive, or volatile, and are regulated by the Resource Conservation and Recovery Act, or RCRA, and CERCLA, or Superfund. These two pie charts here break down municipal versus industrial solid waste. If you look at the diagram on the left, you'll notice that the vast majority, 97% of the solid waste produced, at least in the United States, is industrial. We as individuals in our homes and our small businesses produce about 3% of the total volume of municipal solid waste. So again, as we talked about with air pollution, as we talked about with climate change, individuals are not the problem. Industry is the problem. Okay? Remember, 10 companies contribute 70% of the pollution in our planet. So as you see here, again, we're seeing those same kinds of numbers. Individual human beings are a drop in the bucket of the waste problem. So 3% of solid waste produced in the U.S. is municipal. And of that waste, you'll see on the right side of your screen how those break down. Okay? And if you're looking at paper, glass, metals, and plastics, these would all be things that we would consider recyclables. Then you have wood, yard trimmings, and food, all of which would be considered compostable. So the vast majority of solid waste that is produced municipally can be recovered and used for other things. This is the same graph that you saw just a second ago, but we're going to break it down a little bit more. So 62.4% of municipal solid waste is made up of materials that are potentially recyclable. Okay? And when we talk about recycling, we're talking about primary or secondary recycling. Okay? Primary recycling is when you take something and you recycle it into the same thing. So you take an aluminum soda can and you recycle it into another aluminum soda can. It is pretty efficient. This is also called closed loop recycling. Not a whole lot of waste left over when you do that. Secondary recycling, or open loop recycling, is when you take something, for example, a plastic bottle, and we recycle it into a t-shirt. While we're still using less raw resources, it's not very efficient. You lose a lot of material in that secondary recycling process. Another thing that we have to worry about when we talk about recycling is this idea of greenwashing. Okay? If you are anywhere near your kitchen or anything like that at home, grab something that is plastic. I can almost guarantee you if you turned it upside down, you would see the little triple triangle recyclable with a number in the middle. Okay? So you see a lot of things that are marked as recyclable. Just because it's marked recyclable does not mean that it is. One of the things you have to think about is what that number is. That number is telling you something about the components of that plastic. And some recycling plants can only handle certain numbers or certain components of the plastic. So while something may be marked recyclable, number one, it may not be recyclable in your area, or it may not be recyclable at all. There are large companies, and I'm not going to name any of them, you can probably name them off the top of your head anyway, that will mark their materials as recyclable even though they're not, or mark them as biodegradable even though they're not, because there is no real federal regulation on whether something is recyclable or not. So it's what we call greenwashing. You label something as compostable or biodegradable or recyclable in order to sell to those people who are trying their best to be conscious of those things. But in the end, it's kind of a bait and switch because it's not. You can't recycle that. So in order to kind of combat that, we have I'm sure you've heard of, the 3 R's: reduce, reuse, recycle, right? Reduce what you consume, reuse what you can, recycle what you can't. There's the 4th R. It's refuse. Refuse to be part of the system that makes companies think they can produce these things. The power of the purse, right? You refuse to purchase things that are in single-use plastic bottles, or you refuse to purchase things that have excessive packaging on them. That's part of this idea of becoming a more sustainable consumer that Annie Leonard talked about in your summer reading, that Story of Stuff book. So 62.4% of municipal solid waste is recyclable or potentially recyclable. About 34% of it is compostable. So we can take these things, we can put them in a compost bin, and we can turn them into fertilizer, and we can grow in them in a very rich soil. And then the other 3.3% does not fall into that category. It's not potentially recyclable. It's not compostable. It's possible that this is what we would just call trash, something that can't be composted, can't be recycled, and it's entirely possible that it is a household hazardous item, which we'll talk about in just a minute. So we talked about that breakdown of municipal solid waste. Let's shift our focus to the left side of this slide here, and we're going to talk about waste management hierarchies. Okay? So when we talk about waste management, okay, we have a very finite amount of space on this planet. We have a very finite amount of resources. We don't want to waste anything that we can possibly recover materials from. So we're going to talk about these in terms of most preferred to least preferred in terms of waste management. The most preferred method is to reduce the source materials, reduce using raw materials, and recycle or reuse as much as we can. Okay, so reduce it, reuse it. The next thing is to recycle and compost. Recycling and composting require energy inputs. We still have to melt down the aluminum to be able to make that new can, or we have to melt down the plastic and convert it into a synthetic fiber in order to be able to make that t-shirt. The next one is energy recovery. So we may burn something to produce heat, get that cogeneration process to produce electricity to convert that plastic into fiber into a shirt. And lastly, we treat it or we dispose of it. This is typically the least expensive component, but the most energy intensive. Okay? So when we talk about waste management, in all cases, especially with hazardous waste as well, we want to reduce the amount that we make in the very beginning. Okay? That is the best way to manage waste, especially hazardous waste. Reduce the amount you produce in the first place. Then you want to start treating it. Okay? That's the last kind of thing you want to go to, is to treat it in terms of regular waste. We'll talk a little bit more on hazardous waste in a second, but reduce the amount you produce in the first place is the best waste management system. And there are basically 5-6 methods of waste disposal. The most common one that we use in the United States is using landfills and incineration. There are a couple types of landfills that we'll look at in a second, such as a sanitary landfill and an open pit landfill. So that's one thing we'll do. We'll landfill it. We may burn it and then use that burning waste as a cogeneration process to produce electricity for other things. Incineration has the problem of producing various chemicals that can be released into the atmosphere from this burning process, depending on what you're burning. And there's always ash left over that has to go somewhere. We can compact the waste. We can do the Wall-E idea, right? Put it into blocks, try to build with it. People have done it. We can go through the organic materials and produce biogas, or we can use composting or vermicomposting, which is using worms, to make soil and fertilizer and stuff out of it. So these are the 2 most common methods of landfilling that you'll find on the planet. In undeveloped countries or lesser developed countries, you will typically find what's called an open pit landfill, which is what you see on the right-hand side of this slide. An open pit landfill is exactly what you think it is. They dig a hole and they start dumping their trash in it. And that trash will build up and build up and build up. Some of it may decompose and produce methane. Some of it may contain chemicals that leach into the groundwater and make people sick. It may contain e-waste, electronic waste, which has cadmium and all of these different electronic components in it that can be detrimental. So it's open pit landfill, typically done mostly in developing and undeveloped countries. Most of the landfills in the United States are sanitary landfills. And the thing that makes a landfill a sanitary landfill is the application of with a clay liner. It's typically clay. Sometimes it can be plastic and clay put together. Sometimes it can be layers of clay and sand and clay, with the goal of making an impermeable barrier between the waste and your groundwater. So the goal here is, in a sanitary landfill, you have this liner that prevents anything from leaking down into your groundwater. This includes liquid that comes from the waste as it's decomposing, or rainwater that comes in and filters through. This prevents what's called leachate, Leachate, from getting into your groundwater and carrying those pollutants with it. Most of your sanitary landfills will also have what's called a methane pipe or a methane collector. And what that does is, as these materials are decomposing, especially if they are organic, they are producing methane. And that methane can be captured and it can be used to burn for electricity. Okay? We definitely want to capture it whether we burn it or not, because remember, methane is a greenhouse gas. So if we release it into the atmosphere, we're going to have additional components and problems associated with global climate change. Some places will collect the leachate and will treat it as well. But the big thing for a sanitary landfill is that it has those liners that prevent that leachate from getting into your groundwater. So we've talked aquatic pollution, we've talked atmospheric pollution, we've talked solid waste. Let's talk hazardous waste. So the images that you see here on your screen are examples of household waste that is hazardous, that you have access to in your homes. I'm sure every single one of you has some batteries laying around. You have some Raid or some Clorox or some cleaning spray or some medication. These are all considered hazardous waste. In order for something to be considered hazardous waste, it has to meet one of 4 criteria. And those criteria are that it is toxic, flammable, corrosive, or volatile. Anything that falls into one of those 4 categories has to be managed very specifically and disposed of very specifically. You probably haven't heard this before, but you should not throw batteries in the garbage. Batteries are considered a hazardous waste, and you should not, and technically cannot, put them into a regular landfill. Most people do it anyway, either because they don't know better or because it's harder for them to collect their batteries and take them to a hazardous waste dump site. Waste is regulated by 2 major laws. The first one that is specifically associated with hazardous waste is the Resource Conservation and Recovery Act, or RCRA, RCRA. This is also known as the Cradle to Grave Act. It was originally passed in 1965 under the name the Solid Waste Disposal Act, but was modified later on in the late 70s as we move forward. The Resource Conservation and Recovery Act is also known as the Cradle to Grave Act. It identifies hazardous waste and provides guidelines for their disposal, and specifically holds the producer of that product responsible for the impact of that material from the time it's produced to the time it is disposed of. Additionally, you have the Comprehensive Environmental Response, Compensation, and Liability Act, CERCLA, also known as Superfund, which was passed in 1980 as a response to the Love Canal disaster. and it requires the cleanup of hazardous sites by the owners, provides compensation to those who are affected, and has a fund to do the cleanup itself if the responsible party cannot be found. So these two laws are associated with and highly regulate the disposal and treatment and all those things of hazardous waste in the United States. So this is the common endpoint for pollution and waste: human health and toxicology. So when we talk about human health and toxicology, we're talking about the ways in which the components of our environment affect us. And we're going to look at this specifically in terms of toxicology. Okay, toxicology is the study of toxic substances and how they affect the body or the subject. We're going to look at this in terms of the LD50, or the lethal dose for 50%. We're going to look at dose response curves. We're going to look briefly at some of the major human body systems, such as the nervous, respiratory, digestive, and endocrine systems, and look at some of the most common human toxicants, such as lead, mercury, particulate matter, asbestos, phthalates, and aromatic compounds. Toxicology is defined by the dose, okay? And the dose is typically reported in milligrams of a compound per kilogram of body weight, okay? So if you look here, this is a diagram of the common lethal doses for items that you may experience at some point in your lifetime. The last one definitely not at this point. But 6 liters of water is toxic for you. 118 coffees, espressos, I drink that every day. That's toxic for you. And once you become 21 and you're able to do this, 13 shots of alcohol will be toxic for you. That would put you at a very high alcohol blood level. So the idea here is I want you to think about dose and delivery, okay? It's the dose of the substance and the way it is delivered that is going to be the defining component of toxicity, all right? So the dose makes the poison in this case. So we understand toxicity in terms of this idea called the lethal dose for 50%, or the LD50. And the LD50 is the dose in milligrams per kilogram of body weight that will kill half of your test population in 14 days, or 2 weeks. Most commonly when we understand lethal doses, we are using analog animals. Specifically, we're looking at lab rats, and in some cases, dogs, monkeys. Organisms that have systems that are very similar to ours, that respond very similar to us, that we can make that logical leap that says it affects this organism this way, therefore it's likely to affect us in the same way. Additionally, with a lethal dose of 50%, you have what's called the threshold. That threshold is the dose in milligrams per kilogram of body weight that shows the first effects or symptoms of toxicity. You can also apply this same idea to therapeutic use of medication. In this case, it's called the ED50, which is the maximum therapeutic dose. And then the threshold, which is the minimum dose that demonstrates those therapeutic effects. So make sure that when you're looking at graphs and you see these graphs, you don't immediately assume it's an LD50 graph. You want to make sure that you read the instructions, read the diagrams, to make sure you're not looking at something that is a therapeutic graph rather than a lethal dose graph. So this is a dose response curve, and it's called dose response curve because those are the axes. In most cases, when you're looking at a dose response curve or an LD50 curve, you're going to see the dose reported in logarithmic terms, okay? Because you want this kind of nice logarithmic S-curve looking diagram to help you easily figure out what these toxicity levels are. Okay, so the dose is on the x-axis and is typically identified logarithmically. The response is on the y-axis and is given in percentage, so from 0 to 100%. 50%, that is the number that you're looking for, which is your LD50. Once you get that toxicity up to 100%, everybody dies. That's called your maximum dose. So at that point, everybody's dead. Another way to look at a dose response curve, specifically identifying the therapeutic effect, the ED, your toxic effect, and then your lethal effect. For the most part, you're looking for lethal doses. So you're looking at LD50s. But I wanted to show you this again so that you could see this graph looks very familiar and very similar between the ED50, the TD50, and the LD50. The important thing is to read your graph. Look for titles. Okay? I will never give you a therapeutic graph and ask you to tell me lethal dose materials because you can't do that from that graph. But be clear what kind of graph that you're looking at. All right, so we've defined toxicity. We've defined the relationship between dose and response. Let's talk about the human body systems that are going to be impacted by these components. We're looking specifically at the endocrine system, which makes the hormones that your body needs in order to grow, to function the way that it's supposed to. The respiratory system, the digestive system, your reproductive system, whether you be male or female, your nervous system, and your cardiovascular system. So let's briefly look at some types of toxins that are going to impact your body systems. One of the first ones to think about are what's called mutagens, or those components that will cause a mutation in your genetic code. You have teratogens. Teratogens are those mutagens that will cause birth defects. They're typically those that are introduced to the fetus in early developmental stages, in utero, rather than coming into contact with them after birth. You have carcinogens, those components that are going to make you more susceptible to developing cancer. You have neurotoxins, which are those things that are going to reduce the ability of your neurons and your brain to function in the way that it's supposed to receive and send signals, to store memories, and to interact with the world around you. You have endocrine disruptors, which are components that make it difficult for your endocrine system or your hormones to function the way that they are supposed to. And then you have biological toxins. In this case, we're looking at parasites, bacteria, and viruses. There are several important diseases that you should be familiar with going into the AP exam. And the thing that I want you to be familiar with is what are they and how are they transmitted. Okay? So we have several bacterial infections, specifically tuberculosis and cholera. Both of those are bacterial. Tuberculosis is airborne and affects the respiratory system. Cholera is waterborne and affects the digestive system. Then you have multiple viral diseases. So you have West Nile virus, which is transmitted by a mosquito, so it has an animal vector. You have SARS, severe acute respiratory syndrome, viral, and it is airborne. The current thing that we're dealing with, this coronavirus, COVID-19, is actually a modified form of the SARS virus that we're looking at right now, because it's called SARS-CoV-2. So SARS is viral, it's airborne. MERS, Middle East Respiratory Syndrome, it's viral and it's airborne. And Zika, which is a viral animal vector disease that often causes birth defects. And lastly, you have parasitic infections like malaria. So malaria is transmitted through mosquito bites, and it is a parasitic organism that will get into the body and cause severe damage through multiple body systems. This diagram looks at several specific pollutants and how they affect the body in terms of what body system are they going to impact. Okay, so you'll see in terms of water pollution, we're talking about bacteria, parasites, and chemicals that are most often going to affect our gastrointestinal, our digestive systems, and our nervous systems. Some of our soil contamination is really going to that digestive system. Your particulate matter, all of those air pollutants are going to be largely involved with damage to the neurosystem, the respiratory system, and the cardiovascular system. let's look at some common pollutants that you're going to come into contact with in terms of the AP exam that you should be familiar with. Lead is a neurotoxin that typically comes from old paint or old pipes and steel materials. It has been banned in the use of paint and pipes, but a lot of old buildings and old areas still have it, and it can cause massive neural development delays in children who are exposed to it. Mercury is a neurotoxin and teratogen that most often now comes from industrial chemicals. It used to be a very common component in thermometers. Particulate matter, specifically particulate matter 2.5, PM2.5, is a respiratory irritant that can come from fly ash, pollen, dust mites, anything that is small enough to get into your respiratory system. It can cause large-scale damage, which can lead to what's called COPD, chronic obstructive pulmonary disorder, which can make it difficult to breathe. You have asbestos, which used to be used very heavily in insulation, and it is a respiratory carcinogen. So the asbestos fibers actually get into your lungs, and they develop this kind of cancer called mesothelioma. I'm sure you've seen those commercials on TV of lawyers talking about mesothelioma settlements and things like that. Asbestos can also cause crystallization of the lungs, which is a disease that is known as asbestosis. So you can get that, or you could get mesothelioma, and some people get very unlucky and get both. You have phthalates, which are chemicals that are added to plastics as a softener to make them more pliable. What we have noticed over long-term studies, especially with frogs and other amphibian organisms, is that phthalates are what we call an estrogen mimic. They are endocrine and reproductive mutagens. What happens is the chemical formula and the chemical structure of phthalates mimics the chemical structure of the female hormone estrogen in the body. It can have dramatic effects, especially if a pregnant woman is exposed to high levels of phthalates. There is a disease called testicular feminization syndrome. It happens when a woman is pregnant with a male baby. And what happens is either natural or artificial estrogen or estrogen mimics trigger the woman's body to produce larger amounts of estrogen. And what happens is that changes the development of the fetus. And the baby is born being genetically male, XY, but physically appears to be female. All of the external characteristics look to be female. And the only time that a problem is kind of noticed is when it's time for that child who appears to be female to go through the process of puberty and menstruation, and that doesn't happen. And they're checked out by a doctor, and then they're told, your external is this way, but your internal looks something different. So that can happen. With female babies, and especially if it's in very, very high concentrations, and remember, this is a very rare occurrence in both cases in testicular feminization syndrome and early onset puberty in females. But as we are using more plastics and those plastics are getting into the water, it is going to become a problem that we're going to have to think about a lot more. High levels of estrogen and estrogen mimics in females can lead to early onset puberty. And when I say early onset, I'm talking like 4 or 5 years old. So while these are very rare occurrences in terms of phthalate pollution, because we are using these plastics so extensively, it's something we have to think about. And lastly, you have aromatics. These are things like formaldehydes and volatile organic compounds that have a very strong odor to them. They are typically respiratory irritants, and they can become a neurological irritant in terms of causing headaches and things like that.